Okay, we're going to pass today on trying to do any more slinky spring experiments because those were just a total failure last time. This time we're going to do it by drawing. And if you've got some different size springs at home, you can connect your springs together and replicate what we're learning today. And I'll be keen to see any videos that you manage to produce. What we're talking about is transmission and reflection of a wave as it passes from one medium into another. So the sort of thing we're thinking about is a light spring and a heavy spring. And what's interesting is that in a light spring, the waves travel fast, and in a heavier spring, they travel more slowly. And we're going to look at what that means for the wave that's transmitted into the heavy spring and for the one that's reflected off at that boundary there. This is what it might look like. So when that incident pulse, that incident clump of energy hits the boundary, from the perspective of the light spring, seeing that heavy spring is almost like seeing a fixed end. And so the way that this pulse responds to that is exactly as though it's been reflected off a fixed end. Look, the reflected pulse is inverted. It's flipped the other way up and it's travelling the opposite direction. And if you look carefully, you should notice that its amplitude is smaller because the amplitude is proportional to the amount of energy you've got. Some of the energy has been transmitted and only some of it has been reflected, which means that the initial amplitude's quite big, whereas the smaller amplitudes are with the reflected and transmitted pulses. They both have a smaller amplitude than the incident one. It's also interesting to note that the transmitted pulse here, the one that's passed in to the new spring, stays the same way up. And if we look at how far each of them is from that boundary, note that the transmitted pulse, this one here in the heavy spring, because it's travelling more slowly, it's travelled only a short distance from that boundary, whereas the one in the light spring, because it's travelling faster, it's travelled a bigger distance from that boundary. I'm going to rub these off. We're going to have a look at what happens if we do it the other way. So, this time we've got our incident pulse in the heavy spring and we're firing it off towards a light spring. There's the boundary there, and same as before, this one is relatively slow. The heavy spring, the light spring is a bit faster. We're going to have a look at the effect that has, and this time I'm not going to forget to tell you about what happens to the length of the wave pulse as well. Okay, so that's what the diagram is going to look like, and there's a big difference here. You'll notice that this time my memory jogged and I remembered I need to tell you about the wavelength as well. So we're going to talk about that first, and that's this medium here, the heavier spring. The wave travels slower, and so in fact what happens as that wave is transmitted through into the lighter, faster medium is that the wavelength actually stretches out. So you can see that the wavelength of the transmitted wave is quite a bit bigger than the wavelength of the incident and the reflected wave. And that should have been the same in our first picture. We should have had the wavelength that was transmitted was a little bit shorter. And I think it was, but I didn't really draw your attention to it. Now, the interesting thing to see here is that the reflected pulse, it's as though it's hit a free end of the spring and it's been reflected back without being altered at all. It's the same pulse travelling at the same speed, opposite direction. Key thing, it's not inverted. The transmitted pulse, as usual, is the same way up. The transmitted pulse never gets inverted, and it's travelling faster. So look, it's travelled a bigger distance here than this one has travelled. The amplitude of both of the pulses is smaller than the amplitude of the initial pulse, because, same as before, that energy gets shared between the two different pulses. There's quite a lot written there, isn't there? Let me step you through it. Key thing we need to know is that as a wave passes from one medium to another, the one thing that we can cling on to that's going to be constant is the frequency. That means as light passes from air into glass, it's not going to change colour, which is what we expect. We don't see a different colour when we're outside than the colour of light we see through our windows. And we know from our V equals F lambda, you maths gurus will be able to rearrange that to F equals V upon lambda. And so V1 over lambda 1 must equal V2 over lambda 2, because we know that F1 must equal to F2 because frequency stays the same. V1 over lambda 1 equals V2 over lambda 2. We can just divide that down, and we end up with this here, which is that equation there. That's on your formula sheet. That's why it's boxed up in red. And check it out also, on your formula sheet, it links those to refractive indices. Notice though, V1 over V2 equals lambda 1 over lambda 2 equals N2 over N1. It's the opposite way around. There's no unit for refractive index, but there is a unit for wavelength in medium 1 or medium 2, it's meters, and there's a unit for speed, it's meters per second. That's the equation you'd use if you're trying to solve any change in wavelength, change in speed type problem, or in fact to link it to the refractive index. Got a little challenge I want to put out to you guys. For the soon to be moved on to part of our topic, I'm going to need videos of waves, maybe at sea, going past rocks. If you're living near the sea and you've got a rock that you can see, go down to the sea with your cell phone or your video camera, get us a video so that we can all see what happens to those waves as they pass around the rock, and also what happens to waves as they pass through a gap in the rocks. I want to know what do the waves look like on the far side of that gap. So if you can get me some really good videos, some really good images, that's going to allow us to boost our physics learning. The gold, though, is if anyone can find something that looks kind of like that, where you've got some rocks, then a gap, then a rock, then a gap, then some rocks. That is the gold that we're looking for. If you can find out, you can video. What do those waves do as they come up to those double gaps in the rock? That's our real excellence level learning for this topic.